Seems good. Okay, everyone, thanks for inviting for speaking. I'm going to give the first part of the talk, and you go with the second part of the talk. But we're here to talk about Olmo 3, our latest fully open model. Just a short primer. Olmo project is like Curtis and Zero LLM and many others. We are a project around fully open language models. So people are familiar with these concepts, but we want to share not just weights, but we also want to share training code, inference code, all of our training data, make our evaluations transparent, and write these detailed reports. So we're very much in the same spirit. What we've been doing recently with Olmo 3 and a lot of our projects going forward is to try to release as much more as possible, really thinking about what it takes to reproduce these models, learning from community feedback as to what friction points they have, and then finding pockets of additional resources that we can release that really enables their research. So we've been really supportive of intermediate checkpoints. Every 1,000 steps, we release a checkpoint, but also variants of dataset, not just the final dataset we trained on, but even earlier upstream versions of it. Very smaller versions of the dataset, larger versions of data that you can customize to your own particular training setup. Data tooling, we've been very supportive of also, not just here's our final dataset, but if you want to reproduce the entire workflow of how we arrived at the dataset, you maybe want access to our filtering models, our prompts, our synthetic pipelines, decontamination tools, deduplication tools. All of this is also stuff we're releasing, and as well as frameworks for day-to-day, model ablations that you might run for on like a day-to-day level, week level. We also try to release all these tools for this. Really, the heart of Olmo is that this is built by researchers for other researchers. So we're really excited to see type of research that's being enabled by our work. People are working on attribution techniques for understanding model behavior as a result from pre-training data, using Olmo artifacts to inform policy by studying the LLM ecosystem, understanding, fine-tuning, pre-training their interaction, developing new architectures off of the data artifacts that we release, studying acquisition, like key problems like forgetting, memorization, acquisition. These are really important projects, but also making ourselves accessible to other researchers and being part of the community. This is a screenshot of maybe someone you recognize, where we're just talking about how do you set learning rates? How do you set learning rate schedules? So we really want to be working together with the open community. What we're really excited by is through this many years of work, we are pretty well known, at least with respect to our commitment to open source, releasing data artifacts, even at our size and our resources compared to some of these like very large labs. And with Olmo 3, what we're moving back towards is like setting down our fundamentals around how we think about the entire flow of development through all these many stages. We all know that LLMs are increasingly complex to develop. There's a lot more stages to think about, a lot more algorithms to think about. So this talk is going to use this as a framework to scaffold the topics we're talking about. There's so much to fit, so we're not going to go too detailed, but really we're going to focus on these ideas around as we go through these stages, how do we iterate? How do we think about making progress, looping through, improving the data, improving your model, looking at evaluations, and so on. This is an idea that has allowed us to quickly spawn customized recipes. So as we know, if you want to develop new models, different models that have different properties, such as thinking models versus instruction tree models versus other models, you need to think about working with these patterns, but being able to spot off different branches as you iterate to realize, oh, actually, I need to customize my SFT if I want a different model. I need to customize my RL for a different model. And so why you should listen to this talk. This talk is going to be much more about ideas and iteration patterns rather than particular results. But what we're really excited to share is that Olmo 3, at least on the base model side, is comparable to some of the best open weights only models. We've really had an eye on Qwen 3 there to be as one of our targets. You can see performance-wise across a whole range of base model evaluations. We're right up there. And our thinking model is also right up there with some of the best ones from the Qwen series, Gemma 3 series, Mistral series, etc. All right. But this talk is not necessarily about showing off our results. It's about core ideas. And I actually really appreciated talk earlier today, learning from CERN. It's like the patterns that you presented were really similar to what the ideas we wanted to convey in this talk, which is not necessarily about really brilliantly elegant algorithms or techniques. It's about having a good team, with really good infrastructure, really good fundamentals, and really clean operations. So we're going to try to connect the topics we talk about today back to these principles. So let's go through the whole model flow. Let's start with pre-training and mid-training, which we're not going to talk too much about because everyone's already familiar with these. But I'm going to talk about operations and infrastructure through the lens of one of these topics that isn't really discussed very often, which is data mixing. So what is data mixing? Data mixing is when, as you're scaling these models, you're going to get a whole bunch of data, and you have to make some decision around how much you're going to sample from each data. Some data you maybe don't want to take as much. Some data is really high quality, and maybe you want to upsample. And so you might have some natural distribution of data, like the green black plot, over different pockets of maybe programming languages, different sources of data that you might have. And your optimal might be to solve for some sort of pink plot, like what we have here. So how do you actually do this? Well, one technique that's pretty popular is let's just do trial and error. Let's just launch a whole bunch of different experiments on different sampled proportions over your data and evaluate how good it is. Let's say loss or downstream performance. And when I launch enough of these experiments, you've effectively collected an observational data set, and you can say, let's just try to predict it. If I can fit a model, like a smaller, tinier model, that takes as input the proportion and is accurately predictive of your final performance of your model, then I can just use that as an optimization target. Just solve for the best mix that gives me the best performance. Feels pretty standard. Collect a data set with a whole bunch of runs and you predict. But when you think about infrastructure, this is a nice pattern, but infrastructure allows you to move quickly and confidently. There's a lot of open questions here. How many small models should we launch? What does it mean to launch a small model? How big should this small model be such that it still generalizes? How do you even sample? What does sampling mean? Do I do random mixes? Do I select this carefully? What does fitting a regression function mean? What is this functional form? What should this be? And if you don't get this right, you can end up wasting a lot of compute launching a bunch of runs that don't really predict anything. So an example of investing in infrastructure for data mixing isn't necessarily taking this is everything that closes the gap between this elegant seeming idea to in practice, what you have to do is you have to calibrate your infrastructure. We have to do things such as what we did here, which was, okay, let's just check every single model size from small model up to large and check the correlation with some sort of larger model, both our small model results with your large model results. And we realized that under a sufficiently small model for your proxy model size, you have no correlation. You can't use any of those results. There's a minimum model size you have to invest in before your results actually start to generalize. Okay, so now I know that. Now I know I don't need to waste experiments at a 60 million parameter model size. I could actually still get away with something fairly cheap, but I can't go too cheap. Same thing with, again, on the theme of infrastructure. Regression fit. There's a lot of different results. Lower loss is better in this case, but you could do a sweep over different functional forms for your regression model before you launch your large proxy model runs and figure out what's the best functional form that actually explains this data. Once you have a good functional form, now that becomes your iteration unit that you can invest in for the rest of your site. When we think about operations maybe are reflected less in how you plan out your tooling and configure your tooling, but more in how the team reacts, enabling your team to react well to something's going to go wrong. And here's a screenshot of something that went wrong, which is the first time we ran this result. We were simultaneously also adding new evaluations to our evaluation suite because a pre-trained model should be evaluating a lot of first things, so we're constantly adding. And if we added more evaluation results, this is a plot showing green is as a result of data mixing, result of this mixture proportion, we were getting performance improvements on a bunch of evaluations. X-axis is just each bar is just an evaluation. Red is bad. It's when you're like losing performance against just no mixing as a baseline. And as we added more evaluations, we started realizing, oh, we overfit really hard. Or the mixing idea is overly tuned to like overfitting on these evaluations versus these other evaluations. So we didn't calibrate something correctly. And smooth operations allows us to observe that this is happening and rebalance, reconfigure, readjust so that we can get to some state that allows us for like a healthy balance between what improvements we want and what we're willing to sacrifice. Another part of this is that we reacted to was realizing some of these proportions that we actually want to target. Some of these data mixtures are like science and technology software is actually really, really important. You need to get more of this data. But in the real world, you don't have infinite amount of this data. And if you don't have infinite amount of this data, how do you actually meet to a target proportion of your data that says you need 10%, 20% of your data? Well, you need to repeat. But if you actually knew that you're repeating data, if you repeat enough, you start running into problems, as some people mentioned earlier. And your optimal mix changes if you have limits on what you're allowed to repeat. So one of the ideas that we're thinking about is, okay, well, let's not repeat everything. Let's repeat selectively, some stuff that's maybe higher quality than others. And so if you think about the standard way of repeating data, the standard way of repeating data is basically you define some sort of threshold, let's say on quality of your data. X-axis is quality. Maybe you can sort all your documents into high quality and low quality. And what you usually do is you say, anything above high quality, I'm going to just sample from there and repeat up to the point where I then train my large model. And why not I just always take the highest quality data possible? If I take the highest quality data possible, I set a threshold that's really, really strict, but then I end up repeating my data 5, 6, 7 times. At what point does it start sacrificing performance to your model? So an idea that we started having was, oh, let's do selective quality-aware sampling. Let's define some parametric curve proportional to quality and sample data that's proportional. Like highest quality data, maybe you have some max tolerance on how much you're able to repeat your data before you think the model's gonna come out kind of strange and memorized, and have this smooth progression down towards lowest quality data. You still sample some because you want some diversity, but maybe you don't lean super heavily into it. This idea works quite well. When getting results, works quite well compared to other standard forms of coarse subsampling. And we repeat this idea again to prove it out for pre-training as well as mid-training to show that, oh, actually, even in mid-training, if you want to boost particular capabilities, like if we were particularly weak at the end of Olmo 2 on coding was one of our weak spots, you can use this idea to iterate constantly, looking at the evaluations, looking at your proposed data mixes, and then increasingly iterate until you get to good performance boost that you get at mid-training.
Next step after we worked on pre-training and mid-training for Olmo 3, we focused quite a bit on long context. Olmo 3 is the first model where we really iterated on long context capability, and so it's our first go at it. And long context was really challenging for both our tooling operations, because unlike other parts of developing language models, there's really no consensus across sort of the ecosystem of a fully open model and open weights model. There's the recipes vary different in terms of amount of tokens. Some architecture require very few tokens, either really token hungry. When do you do long context? It's also different across different models. Some of them do it before mid-training, some after SFT. And so the goal here was really like, yes, we want a good long context capability for Olmo 3, but also want to come up with a framework, which is like this how do you make decisions, what kind of tooling we need to iterate around long context. The first thing that we did was long context is notoriously hard to get data for. So what our idea was, well, a lot of long-form content exists in PDF, especially scientific PDFs. Those are generally openly accessible, but because they're PDF, they're hard to turn into tokens. So we first developed a toolkit called OmmoCR that takes a PDF and turns it plain text. This was we had a version one, last year, one at the end of last year. It was really fun to work with. First time using RL for one of these specific parsing application. It's really efficient. Costs about $170 to do 1 million web pages through it. Armed with that, we created a new corpus of about 600 billion tokens above 8K sequence length and 245 billion tokens above 32 sequence length. We have an improved version that is coming out soon that will have even more tokens. This is really crucial for iterating on these recipes. And then based on that, we basically tried to fix tools one by one until we had set up where we could iterate. So where do you do long context extension? How long do you do it for? What metrics you look at? How do you mix some of the data from previous stages in and so on? So we ended up with this recipe, which is we do an extension over 10 billion tokens at the end of mid-training on a 7B model. We mix some of the mid-training data with the long context data, and we observe performance looking. So using this framework, we were able to iterate on a couple of key elements of Olmo 3. So for example, we proved that our PDFs is better data than one of the few open data set for long context extension that was out there, this prolonged data set. We can measure how many tokens you need to get good performance. And we found there's interesting results with like the longer target sequence is, the more tokens you need. We played a little bit with synthetic argumentation for long context extension, and we found them to be quite useful. Different ways to scale the attention, and so on. We even have work in progress that is really interesting around like how architecture, design, and pre-training influence your long context capability. This is not quite ready. Maybe in a month or so, we'll have it out. But it was really nice to come up with this framework, this set of tooling, and then we could iterate on and take a bunch of decisions on. So that was it for the base model training part. I'm going to discuss a few things around post-training. Disclaimer, I mostly work on pre-training. So if you come to me after a question with this, I might just give you a contact email to the right person to reach to. So Olmo 3, on the post-training side, this was the first time building a thinking model. So we had to think quite a bit around how do you support development of these models at every stage of training. So was how do you curate data for SST, especially how do you do it in a modular way? We wanted to have different groups working on different part of data. Then this data has to come together. How do you do that? I'm not going to touch on this presentation, but we had some kind of key insights around preference data and how you use it to sort of boost some characteristics of the model that you care. And then we really had to scale up our RL infrastructure to be able to support this longer generation. So for SFT, we spent quite a bit of time on improving our SFT mix. And specifically, our SFT is mostly synthetically derived from the model. SFT phase, it's a priming phase for larger model. And then for more smaller model, you can really rely on distillation from larger model. So we spent time selecting the right teacher. We were doing a thinking model, so we extended the generation length of these teachers. We added more chat data and precise instruction following data. This complements the Olmo 2 mix, which was more around like math, code, and other STEM heavy setup. And this is the final mix we ended up with. Now, an interesting thing is, Kyle and myself, we've been talking about, we spend a lot of time thinking about operation and think about like how to have the right infra. But sometimes it's really hard to plan ahead of time, and you got to be reactive. Took a screenshot of this thread. If you look at the date, this is October 24th. This was 3 weeks out from our release. And this is me panicking because the model, when I started chatting with it, was behaving really weirdly. And you can see that this results in 267 replies on this thread alone. You can call that operation, but it's really like chaos at that point. But it's interesting, like how do you come a framework of like how when you find this failure later on in development, how do you react around it? How do you organize? How do you diagnose the issue? So in this case, it was when I sent this message, we didn't know what was broken in the model. Maybe it was a pre-training thing, but we zeroed in quite quickly around like this being an SFT issue because we had good ways to iterate with different mixes of data, compare one version with the other. And so we found things that like, we had identity issue, almost thought it was Quen, and that was some data filtering missing. We had some spurious hallucination here and there. Responses were really long, verbose, and the model was unnecessarily yappy. And what we reckoned to all of this was around not having good tools on how to clean data. So we developed a lot of tools and a lot of infra to filter data in many different ways. I have a long laundry list here, but I can discuss more each one of them later if folks are interested. Yeah, the other thing that we had to invest a lot of time with was around like our reinforcement learning setup, because doing reinforcement learning where you're generating long sequences is really hard. The setup face value. It seems really easy. Use some GPUs to generate text, use some GPUs to verify and train, and you send weight updates from one or the other. And then your generation GPUs just send the prompt completions to the trainer. In practice, if you do this naively, you end up with a lot of idle time where first you generate and your train GPUs are waiting, then you train and the generation GPUs are waiting, and so on. And this is really bad for long context because some of them might take very long to generate. You can't start training until all of them are done. So a lot of work was around, okay, how do you pack generation so it happens async from training? And then how do you minimize the interval from when you generate when you start training so you are just a little bit off policy, but not too much off policy. And the results really show. This is like a plot of runtime of like how long does it to train the first version of our RL framework when we started Olmo 3 versus final version in pink. And we have more improvement. We've been iterating on the setup to bring some of the core tech from pre-training into the post-training pipeline. Having the strong infra really allowed us to iterate really quickly across all stages. So this is the progress of model performance across all stages of post-training. And this extended even after release. So we had this release of Olmo 3.1 about 3 weeks after Olmo 3 happened, where we just let the model train for longer and it kept improving on metrics. This was over Thanksgiving break. We were not working, but the GPUs were. So this ends the talk. I think it's slightly over time. But yeah, there's a lot of content if folks want to get in touch with us. We also have the usual 100+ pages paper that everyone is working on fully open language models as written.